Did he say he put like the that in the oh yeah.
Nice. That's great.
I don't know if it's
That's so good. How was the test? It wasn't bad. It wasn't bad. I haven't graded them yet, but just by looking over, I felt. So actually, it was pretty sad. Disappointing. That's one. Or maybe the point was that since you guys came from the first exam, so second exam probably, but usually I could say on a statistical basis based on earlier years, second exam comes out much better for students compared to the first one. But here I felt at least just looking through that it was very similar.
I really do. Yeah, they should definitely. I know. What did I do? Huh?
Oh. Yeah. Hello, good morning. I haven't graded the exams yet. I was really wanting to, but so most probably in the next few days I should be able to finish the grading. Just flipping through, as I mentioned just now, I felt relatively speaking, uh, less, the performance is less than what I expected. That's really, put it, hey, do you guys have any comments or anything you want to say? Alright. Did you guys feel so or? So, okay, so that's good. So many of you saying it was like my usual exam. So it might be just okay. But it is a couple of things I want to point out. One of the equivalent resistance, I expected many to get that because usually equivalent resistance is something everyone in the classroom understands, but most of you got it wrong, maybe because I added too many of them, but I just felt that the basic idea was not there. So I could do the equivalent resistance example here, and the first problem is that the resistance. There many of you did get that right. So those two, I'll just go over it just because probably you will see it around before, and maybe you will pick up something in here. So there was one question here. So first question was you just had resistances, two resistances, 1.5, 2. And this point was given to you, VA, and that was given to you to be VP. You can use just the idea that potential drop is equal to the current time resistance, or pretend that this is a battery. Here, either way, you can do that, but notice that the current that goes in here, I1, has to go into this also. This is like a flow. A water flowing through the pipe, so you cannot expect these two to be different. Current is conserved, or the charge is conserved, so the flow of current has to be exactly the same. So first you conclude that I1 has to be equal to I2, and let's call that I. It is some current I, and that has to be equal to, so now we can construct an equivalent resistance. That's your single resistance or equivalent, and in this case, since resistance will add up when they are in series, that's R1 plus R2. That's A, and that's VB. Whenever VA and VB is given, it's a potential difference that matters. That is all there is. So it is VA minus VB that acts like a voltage that's equal to the current that goes in, that's the I or I1 or I2 is all the same. It is I times R equivalent, which is I times R1 plus R2. So in your problem, I think it was 4.5 volt VA minus 1.5. So that makes it 6. So this is at 4.5 volt, that's minus 1.5 volt. The difference is 6. That most of you got. This is current times the resistance will add up. So it is one was, I think, 1, and the other was 2. That's 1.0 plus 2.0 into 10 raised to 3 kilo ohms. It was given in kilo ohms. So you can get the current to be the same in both. I1 is equal to I2. So that comes out 6 divided by 3. So that's 2.0 into 10 raised to minus 3 amps. Most of you got this VA minus VB idea correct. I think wherever the mistake is happening, the idea was that this I1 is equal to I2 was not recognized by many of you. So make sure you realize that current is like a flow, so that remains the same whenever that is straight wire. Any comments or questions on that? So the other one was equivalent resistance. So there was a battery, there was a resistor R, and there is, I think this was R, R. I think this was R here. So this is again 2R. That's R, and I think there was one more. That's all. That's R. The last one was like a difference. Main thing is, let me call this, for labeling purposes, 1, 2, 3, 4, 5, 6. 1, 2, and 3 are not in series. Okay, for series, there should be nothing in between. There is a bifurcation here that's not in series. 4 and 5 are not in parallel. Okay, so that's one basic thing that takes. So the only thing you can see if you say that these are not in series is that these two are in series. There is nothing in between, right? When you're going from 3 to 6, there is no bifurcation here, so you know that that is in series. So that's the first thing you do. So when you combine those two, remember resistance would add in series, so that becomes 2 times R. And now you have to write a resistance circuit again. So one thing at a time. So this is R, plus 2R. These two have been combined now, so that gives you 2R. These two are exactly the same circuits. The only thing I've done is that these two are combined into one. And then you again ask, is there anything in series or parallel? Again, these two are not in series because there is a bifurcation here. These two are not in parallel because there is a resistance R in between. What is in parallel is that the only thing you can see in parallel is these two or in series. So these two you can combine together enough. 1 over 2R plus 1 over 2R gives you an R. So one from here to here, again, draw the next equivalent circuit. That's R, 2R. And now there is only one here, these two have been combined. Resistors in parallel go by reciprocal. So it's 1 over 2R plus 1 over 2R, so that gives you an equivalent resistance of 2 over 2R, which is 1 over R, but then you have to invert it, so this is R again. Okay. Again, these two are not in series, these two are not in parallel, but these two are in series. There's no bifurcation here, but that's exactly the same idea we had. So you start seeing this pattern here that you can keep repeating. So you did this, and now do the same idea from what you did from here to here. That's here R. These two combined 2R. That's 2R. Now we have brought it down to this level. Again, these two are in parallel. You start seeing this is exactly the same situation as you had here. Like this went into that, so this means this will become R. Again, this. That's your R. That's your R. And finally, those two are in series, so that's 2R. So that's your R equivalent for the whole. So in fact, you could have interesting part in this is that typically this problem is not phrased like this. You can go all the way to infinity. You can keep doing this. And still the answer is 2R. Okay, that's the more challenging one, but it goes exactly the same argument. Just the algebraic relation will be slightly different. But this is the same idea. Yes.
You took that to the would and resist the end line.
And no end, right?
And I guess if you did take it to infinity, would they all be with the last resistance be 2R? And
No, it will be R. Oh, you cannot, yeah, it will be R. That's how you want to imagine it. But you want to say it like this, right? You are never ending. So you don't know, but it is R. All the time it is R. So then you would say, oh, how does it work? So the trick is that whenever you are going all the way to let's think of 1 plus 1 by 2 plus 1 by 4 plus 1. What is that equal to? Anyone? Is that okay? 7, 4, is it?
I think.
No.
Oh, it could be, okay, and it's in the down.
No.
Zero.
It's like saying you first step you go one step, in the next step you go half of it, and then you go half of it, so it could be greater than 1. That's a good guess, that's 2. Right? This is the geometric progression. Geometric progression. So that comes out to be 2, so it is this is exactly 2, so that is 1 plus x squared. That's equal to 1 over 1 minus x. So x is half in here. But anyway, so that's but if you want to, why I brought that in here that there is some kind of similarity. That's suppose you don't know this. Would say that's geometric progression, you would have used the formula, but there is a pattern here that you can take this 1/2 out and now write it as 1 plus the next term is 1/4. I've taken a 1/2 out. So there is a 1/2 again in here. Next is 1/8. That's 1/4 here. You see that? But now if you notice, there is x in itself. X itself is given in terms of x. That's called self-similar. It's like saying u exists and there is a u inside you. It's very, and then you can iterate it. Imagine you are there inside yourself. Then there is no u, right? So inside that there is a way inside because by definition there is a u inside you, and it will immediately go forever. That's a very classic example of infinity. Infinity is usually has a feature that they will be having this pattern which will repeat itself. And here the pattern is x is equal to 1 plus 1/2. That's x itself. And then you can do this algebra. That's x equal to 2. Right? Whenever you have this, you try to use that. So that's a very powerful technique. Now you want to do this with infinite resistance. So what is the pattern that is repeating? So let's say this is your circuit R. Let's say that's we said it's 2R, right? We said that's 2R. And this is again R. And this is 2R. That be like 2. And keep repeating this. Right? So everything repeats from this point on. That means to say that this whole piece here, that's the same as whether I start from here, whether I start from here or here or here, it doesn't matter. Right? Anyway, I will see every term from that. So you will say that this is equal to, so this equivalent resistance will be whatever is the equivalent resistance inside the circuit itself. So that's 2R, R, and now I'll connect this. What do I say this is? That's R equivalent. Is that clear that how the idea is being used? This whole thing is R equivalent, which is also the equivalent resistance of this pole. So that is the answer is there in the problem that you're doing. Again, the self-similarity approach. So if you do that now, so we have these two have to be combined. So you would say R, so R equivalent is equal to R plus I have inverted. So I'll invert this, I'll write it in this form. Let's this is 1/2R plus 1/R equivalent. That's the inverse pointer. So notice there is a R equivalent here, but I have to now move the R equivalent on one side, and that will give me. Like that's how this problem is usually posed. I just cut it off. So that's equal to, just for completeness, R equivalent is equal to R plus. So that is 1 or up here, so R equivalent plus 2R divided by 2R equivalent, so it is 2 times R equivalent. Right. So that's R equivalent minus R. Take this on the left hand side, multiply with that. R equivalent plus 2R equal to 2 times R and R equivalent. So multiply it out. The quadratic equation, I don't know what the second solution will be. So it's the plus 2R minus R, that's plus 2R, plus R, 2R minus R, that's plus R. Minus 2R squared. Equal to 2 times R. So that's R equivalent squared minus R. That's equal to 0. So R equivalent would be equal to plus R plus or minus R squared and minus of minus of the minus, so that makes it plus. That's 4 times 2, that's 8 R squared divided by 8. So that's equal to R comes out clearly, and that is 8 plus 1 is 9. Square root of 9 is 3. So this is R times 1 plus or minus 3 divided by 2. So 3 plus 1, 4. So that is 2R is an answer. There is also one more answer there, which is minus R. There are 2 answers. 2R is clearly the answer in the obvious way that it should be positive resistance. But typically in these kind of calculations, when you are doing infinite quantities, even the negative answer has a meaning. But here we will not address that there. But that was the answer. The 15 good point, but yeah, that's more than what I expected. But at least what you need to know is that make sure you identify what is there in series and what is there in parallel. That's an expectation I have in here. Yeah, that's all. Any comments? Anything I can do to change? To do anything? Seems like you guys are finding it hard. Or harder than last semester. Maybe that's the point. I have a comparison here from the last semester, not even talking about statistical. Usually it's hard to comment what can be changed, so I don't blame you. But feel free to tell me, I think, even later on, to figure out. Okay. So I posted a new homework. Homework 7. Midterm 3 is in the lecture. Actually, we missed a lecture on the election day. Election day is a holiday this time. So Tuesday is the holiday, so we miss that, and so it's the following holiday, November 10th. That, Tuesday is the holiday,
Yeah.
okay. There is a chance that this might get postponed. I'll decide about that before the next class. Primarily because we lost half an hour, and that's a good bit. I need to cover. Talking about this, have you guys seen the video 1 plus 2 plus 3 plus 4 is equal to how much? No. What is 1 plus, we make it slightly different, using the 3. The x, how much is that? That's not a common problem, like don't learn too much from that error. It's very mistake prone problem. Have you seen that video where they say 1 plus 2 plus 3 plus 4? No? I thought that was too popular.
Maybe.
So that comes out to be, believe it or not, minus 1 over 12, and that could be very bothering because as a positive numbers, you get it to minus 1 over 12. But this is how you can, this one is a little harder, but let's do it this one. This one also you would say on when you add a lot of big numbers. At the end, they are very big numbers. They could come out to be a big number. So this is expected to be large, but if you use the same trick, so this is the challenge with that trick that I showed you. This is again 1 plus 2 plus 4, right? Similar, right? This is there inside that, and you would say that this is 1 plus 2 times x. What is x? Right? If x is equal to 1 plus 2x, what could be x? So it comes out to be minus 1, right? So it is not okay. So you add up a lot of positive numbers, you bring out a 1. So that's the challenge with using those tricks. Basic, if you want to avoid these issues, the basic idea is that whenever something diverges, that means grows, it is growing inside, right? Numbers. Then that trick, don't use that trick unless you're very confident, unless you know what you're doing. But when they are decreasing strongly, then it's okay. Then you get, that's a good trick, but just be careful that you don't end up using it in growing series. It's called divergent series. Divergent series is growing, it eventually settles infinity. So just be careful about it. We introduced magnetism, magnetic field, and how force is exerted on a charge due to the magnetic field. We said there is an idea of moving charge. Moving charge means charge itself, Q, times the velocity. So It turns out that it is a moving charge that creates a magnetic field. Which means to say that if you're not moving, you don't participate in magnetism. This is also, if I write this as velocity as length over time or distance over time, and interpret that as the distance traveled by the electron inside a wire, there is an analogy here that this is the same as current times dl. Or current times length. So a current carrying wire, a small element of current carrying wire, or a moving charge, they both create magnetic field. In a lab, this is much more easier. Right? You just have a current, pass a current through it, and it create a magnetic field. But in atoms, inside atoms, when you have electrons moving around, then you want to be able to ask, is this creating a magnetic field? In those cases, this is more powerful method. So, but both are related, a moving charge and a flow of charges, which is the current, they both create a magnetic field, or they get they experience a magnetic force. What we have seen is that magnetic force is equal to Q times V. If it's a charge, that's Q times V crossed with the magnetic field. So this should be thought of together. A moving charge experiences a magnetic field. This is a cross product. Remember your thought, when there is a force, you talk about a movement of a force, what actually helps with rotation. And that's a very similar idea here. It's a moving charge in a magnetic field. You use your right hand rule to get the direction, and that's the force. Since current is given in terms of Q times V this way, this is also equal to I and dl crossed with V. Can write this as a separate equation. So this is applicable for charges. This is applicable for charges. And this is applicable for current. Current into wires. So whenever you see a current carrying wire, a good chance is that there is a magnetic field associated with it. That's a good way to test this, that you take a magnet right next to a wire and it should show these properties. But be careful, notice that if you have a current carrying wire like this, that will create a magnetic field or experience a magnetic force due to that. But if there is another wire going right next to it in the opposite direction, so that's the current I, also current I that's going in the opposite direction, that pretty much cancels out the force because there is a movement dependent quantity here. There's an IDL, where the direction of your length here is decided by the current. So if there are two currents going in opposite direction, it will be hard for you to see this. So most of the time, you have the power cord you have in your computer, that's twisted. So this is how the wire looks like they twist it around, and in that current, in one of the wires, current is going into your computer, and from the other wire, the current is returning back to your power outlet. So if you were to bring a magnet right next to that, even though there is a good amount of current going through that, you will not see this effect. Actually, this is wires are twisted in this form exactly for the reason that to reduce the magnetic effects around it. So for example, if you have a television cable line, they are very sensitive signals, and you do not want magnetic effects or any other wire or some kid coming and playing with a magnet next to a cable wire that should not be disturbing what you see. Right? In principle, it can disturb. So they come up with various ways of shielding wires from these effects, and those are called coaxial cables. So you want that signal to stay inside, and we'll talk about that to a certain extent in 2 weeks live. But what I mean to say is that even though we have moving currents and there are magnetic effects, they not be straight away. If you put it on any particular wire, it will not show it because there are usually canceling effects in there. Sometimes intentional, or sometimes it is just there because of various configurations. That's what we have studied. The summary of this is that this is the expression, but effectively what happens, and that was one of the questions that came up in your exam also, is that if you have a magnetic field, this is going in or it could be coming out or anywhere. And if you have a charge that's moving in, so it is experienced, so there is a magnetic field on the right side of the plane, and there is no magnetic field on the left side, and that itself is a hard concept to bring in. It is typically not easy to have a barrier of magnetic field. Usually there is a gradient in there, especially if there is no material in there. So usually there is a gradient of magnetic field. But if you pretend that in an abstract sense, hypothetically speaking, as a magnetic field you just enter, it's like gravity. You cannot just have a field wall of that. It only weakens out. So if you have such a system, so you have velocity v, a positive charge q comes in, it doesn't experience any force until here. This is a magnetic field. And from this point on, it starts experiencing a magnetic force. And the question is, what kind of force does it experience? This is the velocity. It is in the plane of the board. Magnetic field is going in. And the force in this case, right in this instant, is in this direction. So most of you got that right using right hand rule. There is a force in the upward direction, but the question was about what is the trajectory of this particle. So the moment it turns, now the velocity is in this direction, and we keep rotating out, and it comes out to be a circular motion. That's why trivial statement you have to derive that, but we should be aware that it is a circular motion. So what happens to a charge when it goes into a magnetic field? It goes in a circle. Here it will be a semicircle because it will come out here, and after this point, there's no magnetic field. It will go out here. So magnetic field can be used to reverse the sign of it. But that was not important. But the point was that what the trajectory of this curve, the answer is circle. If you had run circle anywhere around on the page, that was okay. But that didn't pass through. But that's okay because we did it at the last week, and most of you did not say anything, I suppose. But the main message you want to take home is that in a magnetic field, a positive charge or a charge moving with a velocity v will go in a circle. So if you have a circle, the characteristic of a circle is the radius, and how many times do you go in a circle? Those are the two properties that you need to know when you say that a charge is going in a magnetic field. And how many times you go, that's time period, that's equal to 2 pi over omega. And that's a frequency, angular frequency. If you want, or that's also equal to 1 over frequency. Like how many times you go around, so that's time period. And that's frequency. Frequency and time period are the same concepts, or same related concepts. Once you know the time period, you know the frequency. And angular frequency is just the same frequency. You like talk about how many times you go to a particular classroom. You say in this class, you say you go 2 times in a week. What's the time period? What will be the time period? So half a week, right? You go 2 times. It's even though it is distributed 2 days and 5 days are not a very good example. But if you were to average it out, you would be every 3.5 days. That's a time period, but it is 2 times in a week, so that's a frequency. If you want to say it in terms of how many times you go around a circle, you multiply it by 2 pi, and then you get it in terms of frequency. So if you're going in a circle, how many times are you going per second? And that's given by the cyclotron frequency. And that comes out to be only dependent on the properties of the charge, the fundamental property of the charge, Q itself. For example, for an electron, it is 1.6 into 10 raised to minus 19 coulomb, and the mass. No material properties notice, so it is in that sense very fundamental. That is Q and the mass. Nothing else comes into the equation times the magnetic field. So if you ever want to measure magnetic field, a good idea would be if you can somehow indirectly measure the how many times something is going around in a circle. So that's called the cyclotron frequency. So if you're going in a circle here, what the radius are and how many times do you go? And that's your cyclotron frequency. And your radius r is simply given by the velocity, how fast you're going. So it is v over omega c. So that's called the cyclotron frequency. Just to give you a feel for how much this will be, let's say we talked about aurora borealis, the northern lights. If there was an electron and a proton coming in from the sun and they encountered the magnetic field in the atmosphere and they collide with the molecules in the atmosphere, and in that way release light, and that shows up as a green and blue shimmering light. But how much will be the angular frequency when these electrons are going around the magnetic field in an Earth's atmosphere? Earth's magnetic field is 10 raised to minus 4 Tesla. What is the cyclotron frequency? How many times do they go around? So let's say electron in Earth's magnetic field. Remember, we are saying that there is Earth here, there is the North Pole of Earth, there is Canada in here, and all the magnetic field lines go in there. So that's the magnetic South Pole. Right? That's the South Pole, that's the North Pole. Magnetic field lines come out of somewhere in Australia or somewhere close to Australia. That's the magnetic North Pole, even though Australia is in the southern hemisphere. The magnetic North Pole is in the southern hemisphere. So that's your magnetic field lines. And if you had sun here and all the charges start going in circles and they get drift and also along that magnetic field, and they penetrate the Earth's atmosphere here and they collide with the molecules in the atmosphere and release what we see as northern lights. But when they are going in the circle, we can ask how many times do they go? Like, is it slowly there? What is the rate at which they go? So that's a cyclotron frequency. And let's do that for an electron. So that's Q over M times magnetic field of Earth. So that's 1.6 into 10 raised to minus 19 coulomb. That's the charge of an electron. And divided by the mass of an electron, that's 9.1 into 10 raised to minus 31 kg. So that's kg, and that's coulomb. And the magnetic field due to Earth is about 1.0, let's say 1 into 10 raised to the other units for 1 6 digits, so it becomes 9 2. That's 10 raised to minus 4 Tesla. Very weak magnetic field, so it's like weaker than the magnetic field due to a refrigerator magnet. It depends on the distance, of course. If you get very close, refrigerator magnet can be reasonably powerful. So that's equal to the frequency. Remember, that tells you how many times you go around in a circle. So that's let's make it 2, right? 2 divided by, let's say, 10, so that's about 1. That's about 1 digits. So that's minus 23 and 7, 8. So that's 10 raised to 8. What should be the units of angular frequency? Yes, hertz or 1/2. Yes, hertz, that's the unit. So it's often considered angles per second or in circular or angular frequency. You say it is radians per second. And 1/2 is a hertz, so it is radians often you say does not have any units, so it is okay to write it in terms of hertz also, but cyclotron frequency will be in radians per second. So that's 10 raised to 8, more than 1,000,000 times in a second. It's going around the magnetic field. So that's a very fast motion, but it's an electron. It can afford to do that. It reads really tiny, but it goes really fast. These are the kinds of motion we want to get used to, because we're going to talk about light very soon, and there it will be in terms of 10 raised to 14 and 10 raised to 15. This is 10 raised to 8 now. In light, when we talk about frequencies, we will talk about 10 raised to 14 and 10 raised to 15. That's the frequency of light we talk in terms of. It's not very clear frequency of what. We will see that later on. But here we are talking about electrons going in a circle very fast, 10 raised to 8 times in a second. What about protons? One would think that that should also be of that same order, but notice what's the significant difference between proton and an electron is that proton is heavier than electron, not just slightly heavier, it is significantly heavier. It is 1,000 times more heavier. It is like saying Jupiter and Earth, Jupiter and Sun. Sun is 1,000 times heavier than Jupiter. Jupiter is 1,000 times heavier than Earth. So Sun is 1,000,000 times heavier than Earth. So that's a way of remembering it. It is only to an order of magnitude. It's not to one significant digit either, but that's roughly way of remembering it. Same thing. A proton is 2,000 times heavier than an electron. So this is going to be smaller, right? This mass is larger, so that means this will be smaller. So 2,000 means 10 raised to 3 gone. So we expect it to be about 10 raised to 4 or 10 raised to 5. Right, so let's calculate that anyway. Briefly, that is starting from the basic thing. So it is Q over mass times B. This was mass of the electron. This is the mass of the proton. Charge of the electron and proton is exactly the same number. To our understanding, to all significant digits, charge of an electron is exactly the same as the charge of a proton. So that's equal. And this is 1.7, I think. 1.7 or 1.7 into 10 raised to minus 27. Big. And again, one significant is 1. The Tesla. And that's 2 divided by. So that's 2, that's also 2. So that again goes away to 1. So that's equal to 1 into. This comes out minus 23, and this is minus 27 plus 10 raised to minus 24. So that's what we expected. So proton also goes very fast. 10 raised to 4 times in a second. That will significantly fast with respect to what we are aware of, but still significantly slower than an electron. Can we have motions where there are 1,000 rotations per second? How many times does a car wheel go or a car motor go? On your dashboard, it sometimes shows at RPM, revolutions per minute. Do you happen to read that, Trevor? Okay, how much is that typically? 2 or 3, and there is a number at the end written 1,000. So it is 2 or 3,000 revolutions per minute. It is per minute. Good, so it is about 1,000 revolutions per minute. If you divide out by 60. And so let's say about 3,000, so 1 down to 300 divided by 6, that's about 50 revolutions per second. So that's among the fastest. So when you think of a cylinder in a car moving, so it's about 50 or 100 times per second. That's the kind of number of frequencies we are used to. So that's significantly larger, but then electrons really small. It can really afford to. So that's how you want to look at these things. So that's all about force. But we, at the end of the lecture last time, we also introduced the idea of a loop of current. So let's say you have a loop of current. That's your I. That's your I. And the understanding is that somewhere that is a battery, right? So even though I don't show it, so that's an idealized version. Can you have a current without a battery? You can, right? If you have a Van de Graaff generator, yeah, let's think of the potential difference, right? Suppose you have a positive charge Q here, a single charge positive charge Q here. There is an electric field that goes out here like this. Agree? And equipotential lines are perpendicular to the electric field that's down here. Which point is at a higher potential and which one is a lower potential between A and B? There is a higher potential closer to a positive charge and lower potential away from it. So if you were to connect a resistor here, so this is like plus 4.5 volts that showed up in your exam, and this could have been plus 3.0 volt. As you go farther and farther from a positive charge, the potential decreases. 4.5, 3.0, and that's an open circuit now. Will there be a current in this resistor? Is the question clear? Make that more clear. So this is an open circuit, just a hanging wire there. There's a resistor R, and that's your point A, and that's your point B. And relatively close or far away, there is a positive charge, there is nothing else. You measure the voltage at this point, VA to be equal to plus 4.5 volts. And because of this charge, there is a potential at that point. And at this point, VB is lower because as you go farther from the positive charge, the potential decreases. And let's say that's plus 1.5 volts. But they are in air, right? This is like saying you take a computer and keep it here, that's your positive positive side of your wire, that's the negative side of your wire. Will your computer work? Will your phone get charged? If you just keep it in air, it will. It will. Right? There will be a current that's passing in. That was the first question in your exam. There was no charge there, but that's exactly how you do it. To begin with, the charges are stored in a battery for you, but how does that happen? Somewhere there is a mechanical movement which is converting this change in potential to charge stored. So this will have a current that is moving in, but that's very inconvenient. You take a computer and put it somewhere at the right edge, so you form more convenient ways of storing it into a battery. But notice that if you were to have B at this point, there won't be any current flowing in because now they are at the same potential. This is like a water flow. Higher potential, water when it is at a higher height, it is a higher potential. The lower height has a lower potential. When water flows from a higher to a lower potential, it gains velocity. So you can use that. If you're clever enough, you can use that potential energy or the gravitational potential energy into useful work. That means you can store it into a battery. Same thing. This is a higher potential. This is a lower potential. If you have a clever way to make something move from here, it will go faster by the time it reaches here. And when it goes faster, if you have a clever way to store that energy, store that mechanical energy of motion into a battery, then you have found a new way of storing energy. So it is a cleverness that is required, and that usually it is challenging because these are really small charges and they are really hard to manage. Charges are really tiny and they are not easy to control. So that's the challenge, but they are out there. It's very easy to access it. It's just that we don't have a clever way to take it out. Or but we are, so I brought in the idea of that in the loop of current. So you can have a loop of current even without a battery attached to that, but it's convenient to think of it as a battery, and that's perfectly good. Another way of having a current without any charge is what is called a superconductor. What is a superconductor? Have you heard of the word superconductor? A superconductor is something that doesn't have any resistance in it. So once there is a current in it, so provide a current, you open the circuit and give it a battery and a current starts moving in, then there is no resistance. It will never decay off. So there are wires with a superconducting material which is going on forever. Or forever means we know superconductors only for the last many years, so that it's going on only for that many. So the challenge of superconductors is that every superconductor that we have been able to build as of today, it is all works only at very low temperature. By low temperature, we mean it is 273 Kelvin is the room temperature. We are talking about 191, or let's say 200. It's around 200. That's the best we have got. If you can bring it into room temperature, which is an active area of research, then that is a very useful resource. But for now, we are nowhere close to that. So that's another way of thinking. But either way, if you have a loop of current and we keep it in a magnetic field, and the magnetic field here. And that's, they are equidistant. That means that the magnetic field is uniform. So this is uniform. And now we can ask, what is the force acting on this current carrying wire? We said a current carrying wire experiences a force, but now there are four pieces to that. There is one piece here. There is one piece in there, that is here, there. So let's calculate the magnetic force. It is also possible that this could be coming out of the board. It doesn't have to be really in the plane. This could be little into the base, and this could be out into the board, and this piece of the wire could be out of the board. It will look like, in another view, this will look like the same magnetic field, but this could be having, when you see it from the top, this would be in this manner. So that is an angle it makes with the magnetic field. This line here is this piece. And this is little to the front compared to that. Either way, what will be the magnetic force that will act on this? Notice that there is a current going up, there is a current coming down, and this will flip that direction. QB, if one is positive and one is negative, that will be exactly opposite to each other. And if the magnetic field is uniform, that's why it is important that it has to be a uniform magnetic field. In that case, the magnetic force on this wire will exactly cancel the magnetic force on this wire, and the magnetic force, if it was acting in this on this wire, will exactly cancel that wire. So the magnetic force for a loop of wire in a uniform magnetic field is 0. F of B on a loop. So then equal to 0 on a loop in a uniform magnetic field. But does that mean that that doesn't do anything else? It is like an electric dipole. There is no force, but this tries to rotate it. Notice there is a movement here that this force will be in this direction here, and this will be in this direction, so it can actually twist it along. So there is a torque acting on a loop. So we define so I talked about magnetic field and the associated force, but I have not yet strictly defined what a magnet is. So this is the definition of a magnet. So this is more appropriately is the magnetic moment. Magnetic dipole moment. That's a magnet. Anything that has a magnetic dipole moment is what we think of as magnet, or what we see as a magnet. What is a magnetic dipole moment? A current carrying loop of wire. So any current carrying loop of wire. So let's think of it as a circular wire, right? So there is a I going this way and I comes out. And the moment you think of a circular wire, it has a plane associated with it. So that's your plane. And the plane will have a direction perpendicular to that. So you have a circle, and there is a direction that is perpendicular to that circle. That's the direction of the magnetic dipole moment. So it's given by M. So M, which is magnetic dipole moment, it is given by, that's equal to, so what is that equal to? Its direction. It has a direction which is perpendicular to the plane. That's the direction, times the current. More the current, more is the dipole moment, and times area. That is A is area. A, let's say, is area. Area of the loop. And hat is the direction normal to plane of A, plane of loop. Okay. So magnetic moment, so every time you think of a magnet, so magnet has this north and south that we think of. That's the direction of M. A natural magnet that you find in just by mining that typically has this idea of North Pole and the South Pole, but typically when we are doing it in the lab, we use a current carrying wire to build that. So what you would do is that you take a metallic object, for example, a ferrite rod or a nail, like any iron shaped object, and you twist or you just have a wire going around it about 100 times. So each loop will give you a magnetic dipole moment. If you have 100 loops of the wire, then you just multiply that power of the magnet very much, and that's how you will build a very simple homemade magnet. They are also called electromagnets, and its magnetic moment is given by current times its area. So if you have a larger area, you have the larger magnetic dipole moment. So what does it do when you are in another magnetic field? So you have it now, this magnetic dipole moment, the main idea is that it has a M associated with it. So let's say you have a magnetic field. This could be the magnetic field of the Earth. That's your B. And this time we just take that loop of wire, that's your magnetic dipole moment. That property is given by M. That's your magnet. If you hang a magnet in front of the refrigerator that you have, but there is a magnetic field ready-made for you because Earth has a magnetic field. So what happens to that magnet? What it will do is that it will align it with respect to the magnetic field. That's why you say that the magnet always faces the north, because the magnetic field that we have around us, the Earth's magnetic field, always faces the north, or more accurately, it always faces the northern part of Canada, which is actually the South Pole. So the North Pole is trying to point at the South Pole of that, but that is our geographic north. So that is how you go about it. What is the force acting on it? As we said, it is zero, but there is a torque that is acting in here. So the torque on the magnet due to another magnetic field. So this is a torque on a magnet, or magnet, remember, it's the magnetic dipole moment is equal to, it's the cross product. Right? Torque is typically given in terms of a moment, that is M crossed with B. The cross product of M and B give you this. So on the magnitude of the torque, that's equal to M times B times sine of the angle between them. So that's your angle. So that's your angle between them. Vision. And that's what a magnet does in a magnetic field. But now we want to address this whole thing in the reverse. We want to say, how do you create a magnetic field? The magnetic field exerts a force on a magnetic dipole, or a moving charge, or a current carrying wire. We want to ask the opposite question as to, if you have a current carrying wire, can you create a magnetic field or not? And the last 5 minutes, let me introduce that, and we will continue that next time. I should say that the homework that is due on Thursday will be postponed by a day, by not a day, by a lecture. So it will be due on Tuesday now. I will not be able to finish it. But okay, so this is Coulomb's law. Remember, we have Coulomb's law. That's for a charge. And we talk about creating an electric field. Electric field is proportional to the charge Q. It is inversely proportional to the distance R squared. How far is the charge from the source? Right, so that is the charge, and let's say the observation point and the charge, that's the distance between them, and there is a constant in front, which is basically our units decides that. So this is the property of vacuum, it's called the permittivity of the vacuum. Now we want to talk about magnetic field, how magnetic field is created, and this is called Biot-Savart. That's how it's called. The French word is. Okay, and the magnetic field is given by, remember, anything that was a charge earlier, now it is a moving charge. So this becomes Q times B is the, instead of Q, you have Q times B, but we are going to be dealing with current typically. So let's say this is I times dr or dl. I times dl. Let me write it as R so that I can use the R from here. And again, this will be proportional to R squared. That's the main idea. Moving charge or a flow of charges, which is a current, that creates a magnetic field. It is inversely proportional to R, but that's not sufficient. There is a cross product that comes into the picture. We have the moments coming in. So I have to provide an R again here. It is ideal cross with R. And that's an extra R I provided there. So that changes this to R2. Or let me write that as R hat. Okay. So it's R squared. And that's R hat. So that way you get it clear that this is a 1 over R squared effect again. So charge creates an electric field. A moving charge, which is basically a current carrying wire, creates a magnetic field. Its direction is not straightforward. It is given using the right-hand rule. Where you are is decided. So the direction is very twisted or weird. But otherwise, magnetic field wise, it's pretty much the same as your electric field. Instead of a charge, you have a moving charge. What about the constant? This is a magnetic field. It's an entirely different constant that comes in. The 4 pi still is there. But this time, it is not the property, electric property of the vacuum. This is the magnetic property of the vacuum. That's called the permeability of vacuum. So epsilon naught is permittivity of vacuum. And vacuum is somewhere where there is nothing. By nothing, we mean there are only 2 kinds of objects that are either matter, something that has mass, or fields like electric and magnetic field, something that doesn't have a mass. Mass means something that is localized, something that takes a finite amount of space, does not take an infinite amount of space. Electric field spreads out everywhere, all the way to infinity. So that's an example of energy. So mass and energy. So that's if you remove both, that's what vacuum. And mu naught is permeability of vacuum. Okay. This is an electric property for our purposes. This is the electric property of vacuum. That's the magnetic property of vacuum. Just to bring out one point here, if you were to do this multiplication, this seems to be two different experiments done in completely different scenario, electric and magnetic field, and there are 2 properties of vacuum that comes up. And if you were to do this and take a square root of this quantity, it turns out that it has a units of meters per second. And any guesses what that will be? That's a speed. So that's meters per second. Any guesses what that turns out to be? That comes out to be the speed of light. Very good. So that comes out to be 2.99792 458 into 10⁸ meters per second. So what that means is that light is basically an electromagnetic effect. Right, that's the first time you see this, and the moment this was seen, there was a realization that optics that was completely different subject altogether, or you never associated with electricity, is actually an electric and magnetic effect. And we will try to motivate that in the next 1 month, how it is actually an electric and magnetic effect. Stop here, thank you. The homework has been postponed by a lecture.